We're really lucky that today we have our NCAR senior scientist, Gabriele Pfister, here with us. She is an expert in air quality modeling, and she's going to lead us through a little bit about what you might have heard about air quality and COVID and what we can learn about that in a second. Before we get started, though, I just want to mention that if you have questions during the session, please throw them in the Q&A function. We'll be monitoring that, and we will have time at the end for questions and try to get to as many as possible. So Gabby, I'm going to hand it over to you now. Thanks.
Okay, thank you very much. So let me share my screen. And maybe I'll start. So I hope you can all see my screen and you can hear me well. So thank you very much for having me here. I'm really excited to have the opportunity to talk to you about what's close and dear to my heart, and this is air quality modeling. And specifically looking a little bit more about how are we doing it, why are we doing it, and using COVID-19 research as an example to introduce the concept of air quality modeling. So what do we really want to learn about air quality from COVID? The overarching question that's really on everybody's mind is, if the lockdowns that were in place in response or have been in place in response to COVID-19 had a significant impact on our air quality, and if they actually improved our air quality. And there was a lot of coverage and there's a lot of research being done on it. And in a very simple answer, it's very complicated. And the rest of the talk will specifically go on this complexity. I want to show you how we can use models, specifically models in combination with observations, to understand what's really going on with our air quality. And the changes that happened due to COVID-19, they are a unique opportunity for us researchers. It's a natural experiment. But I want to put up a disclaimer that I think I speak for every single scientist, that we rather would have had a different opportunity to get insight into the Earth system than having a pandemic that impacted so many lives. So we make use of it, but it doesn't mean that we are happy about it. So why can we learn something about the Earth system, and specifically about air quality because of the COVID-19 restrictions? Well, the entire Earth system is connected. It connects human activities to the atmosphere, to the land, to the ocean, and this is all feedbacks. Let me show you the example, specifically how air quality is at the heart of this entire complex system. Human activity leads to emissions, but there is more than just human activity that causes emissions. There is also a lot of natural processes that cause emissions. Vegetation causes emissions. There is emissions from land, from the ocean. So these emissions go into the atmosphere. There's a lot of happening then in the atmosphere, and it creates pollution. This pollution has first an impact on human health, also on the ecosystem, but it also impacts our weather. It impacts temperatures through heat exchange. It impacts our clouds. It impacts precipitation. The changes in weather in the following lead also again to changes in our ecosystem and our biosphere, such as on our agriculture. It impacts the occurrence and the intensity of wildfires. It impacts how many emissions come from our biosphere. And this in turn goes back to pollution. So it's really a cycle that we are talking about here. And air pollution is impacted by a lot of different parameters, and in turn is also impacting a lot of the other processes in the atmosphere. When we look back at when the pandemic started, and you looked at the newspapers, there was a lot of news articles that covered air quality and the changes in air quality because of COVID. And early on, it was quite clear, air pollution is reduced, air quality is improving because of COVID restrictions. So these were all the early news headlines. Then with time, it became a little bit more understood that, well, it's not as easy. It's not as easy as a lockdown is reducing our air pollution. it was shown actually and found that there were areas where pollution didn't decrease. There were areas where pollution actually increased. And it was also seen that, well, weather might have had an impact on air pollution, and air pollution also impacted the weather. So that was definitely becoming more clear. But also was much more in the news, and what we became aware of is that air pollution and COVID together are an even larger health risk, and that exposure to air pollution could make actually COVID-19 more severe. This would be a topic all by itself, and I'm also not a health scientist, so I'm not going to touch on that, but I think it's an important topic to bring up also in the context of air pollution. So let me show you just a couple highlights or headlines that you saw pretty early on in the pandemic. And here is just one of those examples. It shows quite beautiful picture of nitrogen dioxide as measured from a space satellite instrument. Nitrogen dioxide is a pollutant which is mostly emitted from traffic and from industry, so it really mostly comes from human activities. And what the image shows is it compares January 1 to 20 for this year with February 10 to 25 of this year. And yes, you can see significantly there is lower values in the February time period. And the headline was nitrogen dioxide emissions over China have plummeted since January. As a scientist, I liked really the attention that's given to air quality. I liked how this image looks, but I got a little bit of a stomach pain when you see that first of all they link this directly to emissions, and that this change that is seen from the satellite instrument is directly linked to COVID. Just taking a little bit ahead, what you see here is what the satellite measures is the concentrations, or what it estimates are the concentrations, and not emissions. Emissions and concentrations are two different things. Other headline that you saw was lockdown impact. NASA satellite pictures of India reveal huge drop in air pollution since lockdown, showing, and if you have seen Andrew's talk before, he actually showed also a part of this. This graphics shows for 2016 through 2020, for actually only a few days of each year, how aerosol optical depths, what we take as a measure of how many particles, aerosols are in the atmosphere, how that was reduced in 2020 compared to other years. Well, first of all, it didn't reduce all over India. There was an increase also in central India that wasn't mentioned specifically in the article. And the question is, was really COVID the cause? Because a lot of other things happened between the years, and specifically if you only look at a few days. So the rest of the talk, I really want to show you what's this complexity in air quality and why we cannot easily just take a picture from last year and from this year or from the week before or the week after and say what exactly happened because of COVID. Okay, sorry. Some troubles moving further. Okay, and the reason for that is because air pollution is caused by much more than the emissions from human activity. So first of all, let me start my laser pointer here. First of all, you start with emissions. And earlier I mentioned there is a lot of emissions from man-made sources, but there is also a lot of emissions from natural sources. They get into the atmosphere and then they get chemically transformed. And these are very, very complex and very non-linear processes. And that means that there is clearly not a direct relationship between the emissions and the sources and what we find in the atmosphere. We also need sunlight in order to have the chemistry happening. It's basically like the energy source that kicks off the chemistry that's happening. Weather specifically impacts what's happening to the chemicals and how these chemical transformations take place. But also weather, topography also impact how the pollution gets transported around and how it gets also lost in the atmosphere. So all these processes we have to consider when we look at changes in concentrations in air quality. Let me take a step back and just tell you a little bit about the most important types of pollutants that we typically talk about. And these are 6. And why these are 6 is these are, first of all, most common. Their health impacts are the best understood. And all of these 6 pollutants are in the US regulated by the Clean Air Act. So the first is carbon monoxide. Then we have sulfur dioxide. Then the one that you've seen a lot in the news related to COVID that was taken as a measure for the emissions from human activity is nitrogen dioxide, NO2, which comes mostly from traffic and industrial sources. We have lead, we have ozone, and we have particulate matter. Mostly you're probably familiar with PM2.5, which is the very fine particulate matter, or we also call it aerosols. Frequently, one or more of these pollutants occur together. So it's not uncommon that you have days when you have high particulate matter and high ozone pollution. And some of them share the same sources and some do not. And what's really making the picture a little bit more complicated is that we have some of the pollutants that are produced directly by emissions. NO2 mostly is produced directly by emissions. But then you have some of these pollutants that are produced in the atmosphere from complex chemical reactions. Ozone, for example, is not emitted. Ozone is produced in the atmosphere when you have what we call precursor emissions of nitrogen dioxides, as well as volatile organic compounds. And they get in the atmosphere, interact, and create ozone. Particulate matter is a mixture of both. There is direct emissions of particulate matter, and then there is also production in the atmosphere. So there is a lot that we need to consider aside from emissions when we want to look at air quality. Let me bring you here one example. I mentioned air quality and weather are closely connected. Here is an example from close home. That was Labor Day weekend in the Denver area. We had the Labor Day weekend, we had temperatures in the 90s. It was extremely hot, close up to 100 degrees. And then suddenly a front came through. And on Tuesday, we had a high in the, well, 40 was pretty optimistic. It was pretty cold and we got actually a few inches of snow. Here I show you observations of surface ozone concentrations on Monday afternoon when we still had the 90 degrees and on Tuesday afternoon when we suddenly had the snow. And you can see that on Monday we had pretty high values of ozone pollution in the Denver area, but there was no pollution at all to be found on Tuesday. And this was not because there was such a dramatic change in the emission. This was simply because of the influence of weather. We also have natural events that impact air quality, and very much on all our minds and very much in the news are now the huge wildfires that we have in the Western US. How that impacts surface air quality, again, here is an example of surface observations. On the left side is an example for 10th of August, 2020. These were particle concentrations on that day over the US before the big wildfires started. And you see that, you know, there is some red values in some areas, but overall, it doesn't look that dramatic. Versus if you go to 15th of September, when the fires were extremely intense and active and, you know, really burning all over the Western US, you can see these extremely high values of surface PM2.5 going way above any health limits. So natural events also impact air quality, and that's aside. Wildfires didn't care if there is COVID or not. Another aspect is also that air quality and emissions change over a number of different time scales. They are not just changing, you know, from one week to the other. What I show here is over many years, from 2000 up to 2019, for different regions in the US, the annual average concentrations of surface NO2. And what I'm depicting here is the change relative to the year 2000, so the change in percentage. But the most important, what you can see is that there has been a steady decline over the last decades in NO2 pollution and in NO2 emissions and in general in man-made emissions. And this is due a lot to emission controls, to cleaner cars. So air quality response to the emission controls. That's actually a success story that we see here, but it also tells you that you have to be very careful when you compare one year to the other. Similarly, emissions vary with the day of the week, for example. So here what you see is one line, the ones with the stars, shows a typical workday emission pattern. And on the weekend, the emissions look very different because we don't have a rush hour, we don't go into work. So also this impacts how your emissions get into the atmosphere and what chemistry happens and what air pollution is doing. We also have changes in seasonal terms, and we also have a large day-to-day variability. Here, just a very brief example of daily average surface concentrations for what we call EPA Region 10. So EPA splits the US into various regions for management, and this includes California, Arizona, Nevada. So if you look from September 2019 to September 2020 at these average particle concentrations, you see, for example, the big spikes here that are due to the wildfires that go way above anything that we observed the year before. You see the seasonal change in ozone, and these are hourly concentrations here actually. So you also see how much variability there is from hour to hour, from day to day. This ozone you see, because it needs sunlight in order to be produced, you see the highest concentrations in summertime. And you also see that NO2, because of chemistry that happens in the atmosphere, but also because of stagnation and different mixing in the atmosphere, there is a seasonal cycle. And there is actually quite a change when you go from winter into spring. So by comparing January with February, there is an underlying seasonal change that we also have to consider. And the last point I would like to make is that satellites do not directly measure emissions or surface air quality. I hinted to that earlier, but the point is what the satellite actually measures is radiation. And then you need very complex algorithms, and you need air quality models to be able to estimate what concentration would be in the atmosphere given the radiation that the satellite measures. I also want to make the point here that a satellite doesn't measure surface air quality. A satellite sees an integrated picture of the atmosphere. So it can tell you something more about the column amount that's in the atmosphere, but it doesn't tell you directly what's at the surface. So you have to make assumptions. And the other point, the last point I want to make in this regard is that our current suite of satellites are polar orbiting satellites, which means over one single point on Earth, they go over that point twice a day, once during daytime and once at nighttime. And most pollutants you only can measure when you have daylight, which means we have the most one measurement a day, and we cannot measure when we have clouds. So there is various limitations. Satellite data are amazing, and they're a tremendous source of information for us, but there is limitations, and we need to be aware of these limitations. So now I mentioned you need models if you want to tease out information about concentrations. Sorry about that. If you want to tease out the information from concentrations from the satellite measurement. Now, what is a model actually? Well, a model is a simplified representation of complex systems that we then can analyze. And Andrew has also hinted on that, and I take just a slightly different approach maybe to explaining what a model is. And here basically what you see is a little toy car, a little model of the real thing that's in the back. Now the little toy car definitely doesn't have all the whistles that the big car has, but it is a pretty good model of the big car. There was actually George Box, he was a mathematician, and he actually made a very good statement once, that was in the 70s, all models are wrong, but some are useful. And why all models are wrong and have certain uncertainties is because there are simplifications and they just cannot get the full complexity. But we use models really every day. We just don't think necessarily that they are models. And arithmetic average, a simple mean of numbers, is a model because it approximates something. We have financial models. We go and we look up directions, Google Maps, there is a model behind it. And then of course we have our physical models that we are now concerned with here in this talk, weather, air quality, and climate models, so that we can predict and analyze extreme events such as storms and hurricanes, that we can look at pollution events, or also predict and project climate change. And a weather, climate, air quality model is nothing else than, it's actually quite a big achievement. It's a simplified representation of the complex Earth system. Basically, we take our Earth system and we stick it into a computer code. How we do that, and Andrew also has, if you have listened to the previous talk, Andrew has alluded on that. So basically what we do is we take our Earth system and we put it into a lot of little boxes. So here the atmosphere is represented by a number of little boxes that are stacked next to each other and on top of each other. And for each of these little boxes, we solve a whole lot of complicated equations to come up with the parameters that we are concerned about. So if you have a weather model and just look at one of these boxes, we take one of these boxes out of here. You have in that box, you solve for all the equations that you can calculate: temperature, humidity, pressure. But then you also have to make sure that the boxes can talk to each other, because our atmosphere is not just an isolated box. So you have to let them talk through all the different directions to each other. So that's a weather model. And if you consider the number of boxes, seems already to get quite complicated. Now let's look what happens with an air quality model. Now we increase the complexity significantly, because now we have to add a lot more processes that the weather model not necessarily cares about, but will also a full-blown weather and chemistry climate model needs actually both, because of the feedbacks between weather and air quality. But let's see what the air quality model all needs. It needs the emissions, man-made and natural emissions. In the boxes, they go inside the box, and then you have all the chemical reactions taking place. And that's actually a large number of chemical reactions that have to take place. There is a lot of compounds in our atmosphere. Our most complex, what we call chemical mechanism, which means is a set of chemical compounds and reactions that we know about, that we can calculate. The most complex chemical mechanism at the moment has a few 100,000 compounds. What we can afford in an air quality model, because of limited computing power, is a few hundred species. So you can already imagine that's one simplification we have to take. We can't put hundreds of thousands of chemical compounds and reactions into a computer model, because we just don't have a computer who could deal with that. So in addition to the chemical transformation and the processes, we have to also look at how these pollutants can be lost. They can get lost under position on surfaces or also in clouds. And then we also have to do exactly what we do with the weather model. All these boxes have to talk to each other. And of course, all these chemical processes we solve on top of the equations that we also need in the weather model. So really what we have is, in a physical chemistry model, because also a chemistry model is a physical model, we have all these processes that I showed you in the box, in a whole lot of boxes for a whole lot of different compounds. And this is all what we have to solve and to simulate all together. So models are extremely, extremely powerful. And they're really one of our very, very important and essential tools in research. But what's really the most powerful tool is if you put models and observations together. For the ones, well, I can run a model, but if I cannot ground truth my model, how can I believe it? I can model a lot, but I have to somehow say that it's actually doing the right thing for the right reason. So we really desperately, observations are essential for us modelers. On the other hand, actually, models are also needed to determine what new observational systems would be the most useful. It's specifically when you design future satellite experiments, that, cost millions and millions of dollars. You want to make sure that you invest into the right thing, that you get a lot of information out of that system. And you can use models for that to run simple experiments or synthetic experiments that will tell you what this new observational system that you design would be able to tell you about your system. So it's really that the sum is larger than its parts. It's really observations and models together. So let me walk you through a very brief, very simple example on, well, first actually just to recap. So how can we use models and observations in COVID-19 and air quality research? Yes, we can actually use them together to estimate the actual effect of COVID restrictions on air quality. We can then tease out the change in the emissions itself. And we also can look at models, validate them for their ability to accurately simulate the impact of these changing emissions, and also work on improving our models given this knowledge. So a very simple example of an air quality forecasting model and how we can use that for COVID research. This is here an example showing surface NO2 concentrations at a monitoring station in Denver, Colorado, which is located right next to a highway, I-25. In black are the observations, and in red is the air quality prediction system that we run at NCAR. We have been running that since last summer. So that's why the time series here shows you summer 2019 through most recent. Now, the important point I want to make sure here is air quality forecast models and the forecasts that they're providing do not consider the emission changes due to COVID-19. They consider a business as usual emission scenario. But what they do is they consider the weather impacts. So when we look now at observations compared to model, the weather impact is accounted for, but not the emission change to COVID-19. So there is some information that we can tease out of it. But what we have here, what you see is, can we trust that model? Because my model, what you see here, is significantly lower than my observations. So something's not quite right. So I need to first understand, why is my model lower? In this case, one major reason is actually quite clear, is that the monitoring site is right next to the highway. So here is the monitoring site located next to I-25, a super busy highway with a lot of traffic. Well, this here, the bigger picture, shows you the model grid box. My model has a spatial resolution, a horizontal grid box of 12 by 12 kilometers. So everything what's happening, I dilute into this big grid box. So I will never, ever be able to get the extremely high concentrations in my model grid box that I see right next to the surface monitor. So it's actually good that my model is lower, because that's what it should be. So this is how I fully understand why I have this bias. So I'm not have to worry too much about this one. But what I can use now is the change in the bias to see how the emissions would have changed. So if you compare summer 2019 and look at the difference between the model and the observations, and you compare that with 2020 and you look at the difference in the model and the observations, you see that the difference in 2020 is much lower. And that's because the observations have gone down more than the model has changed. So now, reminder, the model has a business as usual emission scenario. So by the change in this difference, I can tease out the information by how much the emissions have changed because of COVID. And then if you look at the end of the summer, early fall, then we can see that the bias increases again, the difference increases again. And that's because the restrictions have loosened and our emissions start going back up to the business as usual case. So that's a very simple example. And the rest of the talk, I would like to walk you through a few peer-reviewed studies that show really very well how we combine observations and models in COVID research, COVID and air quality research, and also highlight some of the results that these studies found. So here is a paper from Daniel Goldberg, which was published just in August. And he looked into how much the decline in NO2 concentrations, he used satellite observations for that, was due to COVID-19 versus other factors. And what he did was he looked over the US at various cities. Here, just an example of 4 of the cities that are shown in his paper. And he looked at 4 different methods. And there is, you don't have to try and understand what each different method is specifically about. But the important point is the blue one gives you the estimates of the emission changes if you would do simply something what very early news have done by looking at the time period before COVID and after COVID. In this case, you would have looked at January, February and compared it to March, April. And so this is the blue line. And orange, red, and yellow are methods that start taking more and more into account year-to-year changes, that take into account weather, and ultimately the yellow method takes into account weather as well as chemical feedbacks, which is the most detailed and most comprehensive approach to take. And what you can see is this really simple approach, just looking at the time period before and after, can be significantly different in parts from the more complex methods. So it really tells you that you have to be very careful and consider all the different factors that impact your air quality. And what Daniel Goldberg and co-authors found in this study, by accounting for weather and chemical feedbacks, they found actually that emissions, pollutant emissions, varied dramatically because of COVID across these different cities, from 9 to about 43%. And it really depended how strict the lockdowns were, but it also was dependent on what's the contribution of different sources of emissions. Mostly what has gone down is traffic emissions, and not every city has the same contribution of traffic to their total emissions as any other. So that also makes a difference in these percentages. Another study and another way of looking at emissions is this example by Ding et al., which was just published in September. And they used models and observations to estimate emissions in Chinese cities. And what they did was they used an approach that's called inverse modeling. In inverse modeling, it's basically running the model backwards. So you try and figure out by how much the emissions have to change in your model in order to match the observed concentrations to model concentrations. And by doing so, they found actually that because of COVID, the emissions in Chinese cities were reduced by about 35% on average. But so this inverse modeling is a very, very powerful method, because this gets you really a very good estimate of these emissions changes. With the model, you are able to take into account all the different processes from weather to chemistry. Another study that was also just published in September by Yang et al. In GRL, they use models to estimate weather and climate response because of COVID. In many areas, and this paper focused on Asia, in many areas, the emission decrease has actually led to decreased aerosols, to decreased particle pollution. Now, generally, aerosols have a cooling effect, since they reflect the incoming sunlight back to space. And Andrew has alluded on that in his talk, that the pollution to some degree helps us to mitigate climate impacts. But that's certainly not the right way to address climate change. But anyways, so because of this decrease in aerosols and the impact that they have with the radiation budget, this study found that COVID emission changes could explain about 10 to 14% of the temperature increase in Eastern China in 2020 compared to 2019. So this just shows you that there is this significant impact and feedback between air quality and weather that we cannot just ignore. There were also now, there have been also numerous studies that look specifically into the chemical processes that are happening in our atmosphere and trying to understand how that all changed because of COVID. So we used the models to really understand why some areas showed actually not a decrease in pollution, but showed an increase in pollution. And one of the very early papers that come out in GRL, that was back in May, was from Xi and Brasseur, that looked into using just surface observations of various pollutants and saw and looked at how they changed before and after COVID. And what they found was that while, and you see that in the graphic here, while the emissions dropped with the beginning of the lockdown, like NO2, well, there were some pollutants that increased, specifically ozone. You saw a dramatic increase. Now, this study only used observations, and so the authors were only able to make a hypothesis why these changes happened. Some later studies used an integration of models and observations and took a much deeper dive into what the issue is. And list just here of these, two of these studies, Li et al. And Huang et al. And what they find that, first of all, that PM 2.5 increases that happened in northern China during the lockdowns were due to an unusually high humidity and stagnation. Stagnation means that the air doesn't go anywhere. It's just sitting over in the area and nothing gets mixed or moved around. And those are some very special heterogeneous chemistry on the aerosols. Heterogeneous chemistry, see that as something where gas phase pollution can interact with solid or liquid phase pollution. They found further that because of the reduced NO2 and the increased ozone as a result of that, and maybe I need to explain it a little bit more, what happens with ozone, I told you it's only produced in the atmosphere, it's not emitted. And when you have very, very high levels of emissions of NO2, what happens is actually ozone isn't created, rather it's actually destroyed. So in China, we have extremely high levels, generally in a business as usual, of very high NO2. Now with the lockdowns, we suddenly brought the NO2 down, and now suddenly we were able to get out of that regime where we are eating up ozone to producing ozone. So that's why ozone increased. But because of ozone increasing in the urban areas in China, that increased our photochemical activity in the atmosphere, and that curbed the secondary production of particle pollution and also added to this increase in northern China. So there is a lot of feedbacks, and if my explanation seemed a little bit complicated, and why this picture is a little bit complicated is because it is really a complex interaction. And last example that I would like to show is some very preliminary work that we at NCAR have also started. And we are using models here to evaluate different COVID-19 emission scenarios and project impacts on air quality and climate. So we are using here a fully coupled global chemical climate model, which means it simulates weather, it simulates all the chemistry, it simulates the land and the ocean. And what I'm showing you here is just some very first results looking at the changes in nitrogen oxides, which is nitrogen dioxide plus, by comparing simulations with adjusted emissions to a business as usual scenario. The adjusted emissions, there's various groups in the world who are developing adjusted emissions that consider the restrictions that happened during COVID. They are using a method that I showed earlier, this inverse modeling with observations. They are using activity data such as traffic counts, but there is also a great source is also the Google mobility data or the Apple mobility data that are frequently being used. And so we are testing these different emission inventories on our model and then see what impact it has on air quality and on climate. And what's just why I bring up these pictures here is from this very first runs is what you can see is in January, the bigger changes happened only over China, because back then, you know, Europe or the US were not really hit by the pandemic yet. But then you see with each following month how these changes start spreading away just from Asia and reaching all the other parts of the globe as well. So I think I'm doing fairly well on time. So let me just leave you with a few takeaway messages. COVID-19 is an enormous tragedy. Nobody really wanted to study it, but since it happened, we as scientists are using this as a real-world experiment to advance our understanding of our complex Earth system and also to advance our modeling capabilities. Yes, significant changes in emissions and also air pollution were observed, but relating the entity of these changes to the COVID restrictions is not as clear-cut. It's a complex process. The most bang for the buck, the most information you really get when you combine physical models with observations and study these impacts and learn from that. The studies that have been done to date demonstrate that there were large changes in emissions, that demonstrate complex feedbacks on air pollution, and also the important role of weather. And there is a lot more studies coming out and a lot more progress will be made on our understanding. And as I've mentioned that before, COVID is an enormous tragedy, but the knowledge that we gain from studying air pollution during COVID will help us to gain a better understanding, improve our models, and eventually provide more robust projections of future changes in air pollution, if this is for the next year or if this is on climate scales. And with that, I say thank you very much.
Thank you so much, Gabby. Just as a reminder to folks, if you have questions for Gabby, please throw them in the Q&A field on the Zoom. And we already have some to get you started. So Gabby, you gave a few great examples there at the end, particularly about how you can use a model and observations, but to really figure out how much did emissions change or how much did China warm, for example. This question is asking for a little bit more specifics on how the change in emissions due to COVID lockdowns can actually improve the air quality models. Can that information help you actually make the model better?
Yes, because it's you can see there's an instantaneous, and I apologize, I'm trying to stop sharing my screen. And somehow my mouse with the laser pointer, I cannot get it over there. So I apologize. I have to leave it for now like that.
It's okay, they can soak in the conclusions, Gabby.
Okay, yeah, sorry. And so the thing is, yes, see it as an instantaneous experiment to test how well the different processes in our model work. An emission change, typically when it happens over a long period of time, there is so much else that happens, and there is so many other conflicting processes that we need to evaluate in our models that it's hard to single out just the emission process. Just imagine, climate is changing over time. So we just cannot single out the emission change that easily. But with COVID, we got a vision, we got basically a natural experiment, as if we, let's say, for some regions, start transferring our car fleet, half the fleet, into electric cars. Can our models really simulate scenarios like that? Typically, we can't do them because typically we just, we run a sensitivity experiment with the model, but we have nothing to evaluate. Now we have this information about what changed, and we see what changed in the atmosphere. And so, yes, we have a very isolated process, basically, that we can now evaluate in our models.
Thank you. So in some ways, you're using the reduction of traffic as an opportunity to have observations to test something like, what if it wasn't less traffic because of COVID, but it was electric cars?
Exactly.
Yeah, that's fascinating. Here's a really interesting question, Gabby. Could a reduction of pollution due to the COVID lockdowns have contributed to the heat waves and associated fires on the West Coast?
Now, not that I would have done studies on that, but I have to say, first of all, the impact on particles we have typically, aside from wildfires, rather low particle control. Oh, thank you very much for whoever was able to kick me out of here. So in the US, we have typically rather low particle concentrations, aside from wildfire periods, and maybe in wintertime when we have really strong inversion periods. So the impact on temperature is rather small. And this extreme heat that we found in 2020, this cannot be explained by the small reduction in particle pollution that happened because of the emissions in COVID. So even without doing a detailed study on that, I can tell you that the extreme heat of 2020 is not explained by the reduced particle pollution.
This is sort of a question from the other side of that, Gabby, another wildfire question, which is, how do the models take into consideration things like this year being a record wildfire year in the Western US?
Oh yes. I mean, we take in order. So the forecast models, what they have is for most man-made emissions, traffic, industry, etc. They take a business as usual scenario. Well, wildfires, there is no business as usual. No year is the same and no day is the same. So what we use is we use satellite data that observe what we call fire counts. So they look at hotspots over the globe. And we can take that information to develop emissions of wildfires in near real time. So yes, they do, all our forecast models consider what we call near real-time fire emissions. They do not predict a fire that happens tomorrow. You can imagine that's pretty tricky to do. But they do predict what happened. Let's say our model gets the fire information from about a day before, and then it keeps it constant throughout the forecast period. But yes, natural emissions such as wildfires, episodic emissions, there is no business as usual scenario, and you consider them in the most near real time as possible.
Thank you. So here's one. What are the main sources of lead in the atmosphere?
Oh my God, there is some lead comes from wildfires. But otherwise, it's mostly just from left. Really, I actually wouldn't know that it's even still a big problem.
Without leaded gasoline anymore, that must have changed it a lot.
I don't think that there is enough in the gasoline that it really has a big impact. So, but there might be certain industries I must admit that I really wouldn't know what it is. This is, guilty as charged. Lead has no real interest in chemistry. So it's kind of something.
It's not the most exciting of the pollutants.
It's not really anything that's in general of a big concern anymore as an airborne pollutant.
So we have a question that asks, you had mentioned the preliminary NCAR research. What is your timeline for publishing these results? And then also, how long do you think it will take for models to be updated and improved? Is that something that takes years, months?
That all depends. So our NCAR research, I would say it will probably take a few more months before we have a peer-reviewed paper out. Simply because we still need to run a few more sensitivity experiments. We spend a lot of time on evaluating the model with satellite observations and surface observations before we even do an in-depth analysis. So it might, and then the peer review process takes also a while. So I would say probably a few months before we have really peer-reviewed paper out. But I think, if we have something very interesting that comes out sooner, it will be presented, let's say, at the HEU or at other conferences. To improve the model, it all depends. As you can see, is some of the inputs we have been able to improve already faster by developing emission scenarios for COVID. So that's one input. There is already some work being done on improving the chemistry, the chemical mechanisms that we have in the model. That can, for certain, specifically in China, we had seen extreme changes in what's happening in the chemistry. And there is work done, not necessarily in 3D models, but what we call in single box models, where we can have a lot of I talked earlier, the most explicit mechanism with a few 100,000 compounds. We run it in a box model, and we run scenarios in there. And so I would say probably in a few months, you might have already some first new insight into what other chemical reactions and compounds you need to include in a 3D model to fully characterize some of these changes. And then, some changes, specifically when you start looking at cloud interactions with particles or something, it might take months to years to improve the models. I can tell you just, COVID was a natural experiment. We also have designed experiments that are often happen. And one thing that we do a lot is field campaigns, where we go out into the field and we take very targeted measurements to look at very specific processes. And it takes typically between 3 and 5 years before you get the most of the results and most of the research done on a field experiment. So it's also for COVID, it will take years for us to fully analyze and make full use of this experiment. Hopefully it doesn't take years for COVID to get it.
Yes, hopefully. So Gabby, I have another question, and I'm sort of laughing because I think I suggested you take out some slides that would have answered this question, but it says, please describe the process of converting the satellite radiation sensor data into the NOx concentration maps.
Oh yeah, okay, that's, yeah, you took out my slides.
I'm sorry.
No problem. So and I'd be more than happy to talk also more offline because that's a really complicated process. So as I said, you measure the radiation from the satellite. Now you measure the radiation in various wavelengths, right? And every chemical compound that's in the atmosphere has a certain signature where it absorbs. It absorbs in some wavelengths and more than in others, and in some it doesn't absorb at all. So you need to look at this pattern, what radiation is absorbed by this radiation that comes from the sun, goes all the way through the atmosphere, is reflected at the surface, goes back up and goes back to the satellite. So you need to see how these signatures change between what the sun radiation is and what the satellite sees in radiation. So you can imagine for that, you need to know what is in the atmosphere. You need to know what's the reflectivity of the surface, how much of the solar radiation is reflected back. You need to know where do I find the NO2. So you need a first estimate of, is all the NO2 at the surface, which will of course change how the radiation goes through the atmosphere, or is the NO2 higher up in the atmosphere? So there is a lot of assumptions that you need to make and that go into what we call the retrieval code. And I'd be happy to talk more offline, and it will be probably easier to do some drawings and show how that exactly works. But basically, you need to really follow the transfer of radiation, how it goes from the sun through the atmosphere and back up to the satellite.
Well, and Gabby, this sort of leads into another question that we have, which sort of goes back to the very first headlines you showed in your talk, which is, even if I didn't fully understand what you just said, I definitely came away understanding it's very complicated for a satellite to try to tell you what's on the ground. So I'm wondering, like, as a former reporter myself, if I saw those two side-by-side satellite images, which are quite stunning, like, I want to write a story about that. Like, and there was significant change that was due to COVID. You just couldn't right away say how much. Do you have any advice or suggestions for journalists and science writers looking to cover what is news, but do so in a way that you wouldn't make your stomach hurt as a scientist when you opened your paper in the morning?
Right. And I think actually, it's totally understandable. And I think it was important. And I really appreciate all the coverage that came out, because it was important to see the changes in air quality, but it also helped really raise awareness that air quality is a problem that impacts all of us. I think what I just would like to see is that there is nothing wrong with showing these images, as long as there is some sort of, okay, but caution. There is, it's legitimate to say that some of that reduction that you see is because of COVID. but not necessarily everything is COVID, because, there is changes with the weather, there is other impacts. So just acknowledging that there is limitations in a simple comparison like that. And I don't think you need to go through the complexity of saying how, the radiation transfers through the atmosphere that a light and does whatnot, and that you need 100,000 chemical compounds in the atmosphere. Just acknowledging that this is an estimate, that there is definitely reductions, but that it takes more diving into the issue to understand exactly how much.
So Gabby, now that, it seemed like just in the last couple months, September, August, some of these peer-reviewed papers are starting to come out. Have there been impacts related to the COVID lockdowns, emission reductions that surprised you as an air quality scientist? Were there things that seemed strange?
Yeah, I think the first that probably surprised to some degree a lot of us researchers was the changes in China. The thing is, we knew about China that reducing NOx will increase ozone, but specifically how it also gets the feedback on particle pollution and the dramatic effects that we saw, I think there was a lot that surprised us. The other surprise was actually that there was in parts very little impact on specifically things like ozone pollution in the US. And that just demonstrated to us what is not too surprising, but was still kind of shocking to see that, in Colorado, the traffic changed quite a bit, but there was very little impact on ozone, that it's actually so much more complex and not as straightforward as reducing emissions and changing pollution. That sometimes you need to, that maybe we didn't turn the right knob to change the ozone pollution. That's the other thing also that we learned. So there is more that we need to look into than traffic.
So I think we have time to squeeze in just one last question, which is, since it's so complex to model air quality, will we ever be able to forecast it more than a day in advance with skill?
No, well, the thing is with skills. First of all, with air quality forecasting, we rely on weather forecasts. So we can only be as good as the weather forecast. So that's for sure. So yes, I can put all the blame now on the meteor. The one thing, otherwise we could predict air quality. We can predict it at least as far out as a weather model. But one thing that we cannot predict is the impact of chaotic events, such as wildfires. Or let's say we also have a harder time. There was a really interesting example from the forecasts we run in India, where we predicted a very high pollution event. Because of that, the government took action and put restrictions in place. And suddenly our forecasts were wrong. So we cannot predict this very short-term changes, such as, one day to the other emission controls, wildfires, or COVID.
That's a really fascinating point, Gabby, that when you predict a really bad hurricane, your prediction won't change the hurricane. But if you predict a very bad air quality event and people take action, then your forecast looks wrong.
Exactly. About that. That's actually something I'm really excited to see, that your forecast is wrong.
Right. Well, Gabby, thank you so much. That was wonderful. And I'd really like to thank all of the attendees who gave us an hour of your afternoon. And we hope that the rest of your ScienceWriters conference is wonderful. Thank you.
Thanks, everybody.